This is the beginning of section 8.3, which involves trigonometric integrals. This section will be kind of lengthy just because of the length of examples and the number of examples I want to show you, so plan accordingly. So in section 8.3, we'll study different forms of integrals. So some of the forms will look like this or this, where m, the exponents, are positive integers. So what you'll want to do is you'll want to try to break these down into different combinations so that you can apply the power rule. So if, for example, you have this function here, sine of x to the 5th power times cosine of x, what you can do is use a u substitution. If you let u equal sine of x, then du is cosine of x, which is in here. So what you have, if sine of x is u, then you have u to the 5th, and then this is du. So this is quite easy to integrate. Okay, so those are the things that you'll want to try to identify. So if you have sine of x times cosine of x to some powers, then think about different ways you can break this up in order to integrate easier. So here are a couple of different identities for you to remember. If you can remember, this Pythagorean identity is one that students often remember, but the power reducing formulas are not as easy to remember, so you might want to jot those down so that you can recall those. The reason these are nice is because integrating sine squared of x is quite complicated, whereas this here is much easier to simplify because you can write this as 1/2 minus 1/2 cosine of 2x, which can be integrated quite easy. So this slide here shows all these different guidelines for evaluating integrals. And I don't want to take the time to just read it to you because that will just make this video longer. So what I'd like you to do is pause this for a moment, and I want you to read through each of these guidelines. These guidelines are difficult to remember, but hopefully you'll start recognizing some patterns when you are doing these. And of course, you can always have this, this chart near you when you are working on your homework. So there are a couple things here. If sine is odd and positive, or if cosine is odd and positive, or both sine and cosine are even and non-negative. So these are kind of the things to identify. I'm just going to jump straight into the examples. Here is the first example. It says find the indefinite integral of this here. Okay, so if you look at this, you have cosine and sine, and the cosine is odd and positive. So since cosine is odd and positive, if you refer to the previous slide, you'll see that we should really convert cosines to sines. So that's the approach that I'm going to take in this example. All right, so when I make this conversion, what I want to do is I want to rewrite cosine, but I'm only going to break it down so that I'm saving a cosine. So here's how I will rewrite this. This will become the integral of cosine of x times cosine squared times sine of x to the 4th dx. Okay, now looking at this, I have a cosine squared of x, which I showed you on a few slides ago. This we can apply the Pythagorean identity to this. So I can rewrite this as the following. The integral of keeping this cosine of x. This is the same thing as saying 1 minus sine squared of x. Now again, I'm just applying the Pythagorean identity, the one that says sine squared plus cosine squared is equal to 1. So that's what I used there. And then this is multiplied by sine of 4x dx. Now this is a little wild and it takes a little bit of time to get used to. So I understand that. Just make sure you go through these examples. So now what I'm going to do is I'm going to distribute this so that I have all signs here. So I have cosine of x times sine of x to the 4th minus sine of x to the 6th power dx. Okay, so now moving along, what I can do is distribute this cosine. And if you want to do that in one step, that's perfectly fine. So now I have, writing this, sine of x to the 4th times cosine of x minus sine of x to the 6th times cosine of x dx. Now what I can do is I can separate these into two separate integrals. So when I do, I have the first integral minus the second integral. And now we just integrate these. And what's nice about this is that I can use a u substitution like I showed you back in the beginning. So here I'm going to let u equal sine of x. So if u is sine of x, then du is cosine of x dx, which we have. So when I integrate this, this is really u to the 4th power du, which is 1/5 u to the 5th. We do the exact same thing over here. So over here, instead, you're going to let u equal sine of x once again. And then you'll have u to the 6th power over here that you need to integrate. So I'm going to wave my hands a little bit in order to make this video a bit shorter. So when all is said and done after these u substitutions, you should have 1/5 sine of x to the 5th minus 1/7 sine of x to the 7th plus c for the final answer. So the hard part, once again, is the algebra or the trig that is involved to rewrite the integrand so that it becomes something that you can integrate. All right, this problem is very, very similar to the previous one. The only difference is I only have sine here. So take note that the power of sine is odd and positive, and according to my little guidelines, if sine is odd and positive, then you want to utilize guideline number 1 and convert to cosines. Oops. So what I'm going to do is I'm going to rewrite this but I'm going to just pull out one of the sine of 3x's. So this will be rewritten as sine squared of 3x times sine of 3x dx. That's the exact same thing we started with, but now this can be converted by applying that Pythagorean identity once again. So this becomes instead 1 minus cosine squared of 3x times sine of 3x, which is just this guy here. Just like before, I'm going to distribute this. When I do, I have the integral of sine of 3x minus cosine squared of 3x times sine of 3x dx. So I have two terms, so remember I can separate this into two separate integrals, and when I do, I have the integral of sine of 3x dx minus the integral of cosine squared 3x sine 3x dx. When I integrate this, you should be able to integrate this easily to get a negative 1/3 cosine of 3x. Plus, over here, this one's a little more complicated, so let's take a moment to integrate this. This one is very, very similar to the previous example, whereas I want to let u equal cosine of 3x. Okay, because if u is cosine of 3x, then this is just u squared. Okay, so if that is u, then du is negative 3 sine of 3x dx. So I'll need a negative 3 here. I will undo it on the outside. So I end up with, let's see here. When I integrate this, I have 1/3 times the integral of u squared du, which gives me 1/9 u cubed. So I'll just plug that back in, and this will be positive here. So 1/9 of cosine cubed 3x plus c. And this is the final answer. So now we're moving on to different trig functions, namely secant and tangent. So if I have something of this form, now I have these guidelines. So once again, pause the video and read through some of these guidelines here. Do the same thing here because this just continues. So it kind of tells you some different things to take note of. When the first 4 guidelines do not apply, then try converting to sines and cosines. Okay, so let's go ahead and look at our first example that is in terms of secant and or tangent. So here is our first example. It's secant of pi x cubed. And one thing to note is that the power of secant is odd and positive. So if that is the case, what we want to do is we're going to want to use integration by parts. And what we'll do is kind of rewrite this again. So we'll call this secant squared times secant of pi x. So using integration by parts, I want you to remember that the integral of u dv is equal to uv minus the integral of v du. So in this case here, applying integration by parts, I've rewritten this because what I want to do is I want to let dv equal the more complicated trig function, which is this. So if this is dv, then u is secant of pi x. So from our previous lesson, oops, this should have a dx, we should be able to find v and du. So here, if this is the derivative, you should know that the integral of this is 1 over pi tangent of pi x. If you don't know that, refer back to your rules of integration. The derivative of this then is pi times secant tangent of pi x. Okay, so here we go. Now that we know all of these pieces, we are going to apply integration by parts. So this function, what we started with, is equal to u times v minus the integral of v du. Oops. Sorry about that. Secant of pi x, tangent of pi x. Sometimes it's nice to put the argument in parentheses. All right, so now we just have some simplifying that we need to do. So in this case, I'm just going to move this 1 over pi out. Over here, this is all multiplication, so I know that these pi and 1 over pi will cancel out. And then simplifying this, I see that this becomes the integral of tangent squared pi x, because I have two of those, times secant of pi x. And this is nice because this tangent squared, I can go ahead and convert this to secants. And that's nice to convert that to secant so that I have the same trig function in here. So converting this, I get the integral of secant squared of pi x minus 1 times this secant of pi x. Just like before, we will distribute this. So this is secant cubed of pi x minus secant of pi x. All right, so now in this case, just like before, I can separate this into two separate integrals. So this becomes the integral of secant cubed pi x minus the integral of secant of pi x. Okay, so we now need to continue to simplify this. All right, so what I'm going to do is I'm going to get a new slide so that I have some more room. And what I'm going to do is I'm just going to rewrite this is equal to this minus this. Okay. Okay, so as promised, this is what we had. Now, we are subtracting those two integrals, so we're really distributing that subtraction sign. So this integral becomes a positive. Okay, so this is where we get a little mathy. Now, I want you to notice that we have a pair of like terms. This here is the same as this. So what I can do is combine those. I'm going to add these. And you're probably thinking, how in the world am I supposed to know that? Well, it's okay. We're taking baby steps here. Okay, so when I combine these, now I have two of them. I'm just combining like terms. It's just algebra, right? Okay, so now this is equal to this. And this. Just bringing this down. Okay. All right, so now we integrate. So this here you should know from your chart, or I don't know, you should know this antiderivative. So this here is equal to the following. This antiderivative is 1 over pi times the natural log of the absolute value of secant of pi x plus tangent of pi x. Oops, this is absolute value. And then plus c. Now you are probably thinking, mind blown. You can refer to number 12 on the basic integration rules chart for that. Okay, so what I have is this equal to all of this. So a couple things. Remember, what I want to find is this. So what I can do is I can divide everything by 2, and that will get this by itself. I can also take this GCF out. So really, what I end up getting, dividing by 2 here and here, and taking this GCF out, I get this times this plus this. And this is the final answer. How fun was that? Okay, let's take a look at something a little different now. Now we are going to talk about integrals that involve products of sines and cosines, where there are two different angles. So hopefully from your trig class back in the day, you remember these product to sum formulas. And chances are you don't remember these product to sum formulas, but here they are. Pause the video, take a look at them, and we will apply these rules in the next example. So here I have sine of 8x times cosine of 7x. And if I look at this, this looks like the second item in the chart from the previous slide. So just plugging in to this formula, it is just a formula. So this is equal to 1/2 times the integral of sine of 8 minus 7x plus sine of 8 plus 7x dx. Okay, so just applying that formula. So simplifying, I have 1/2 times the integral of sine of x plus sine of 15x dx. So I'm really integrating this and then integrating this, and when I do that, I have 1/2 times negative cosine of x minus 1/15 cosine of, cosine of 15x plus c. If I want, I can go ahead and distribute that 1/2, giving me this as my final answer. Which hopefully you didn't think to be too complicated. Okay, let's look at our last example. Our last example involves a definite integral this time. And again, this is a definite integral because I have these limits of integration here. So looking at this, tan squared of x, I don't have any rule for tangent squared. So what I'll do is rewrite this using a Pythagorean identity. So this becomes the following. I'm going to write tangent squared as secant squared of x minus 1 dx. Then integrating this, the antiderivative of secant squared is tangent of x minus x. We will evaluate this from 0 to pi over 3. We no longer need the plus c because this is a definite integral rather than a definite integral. So plugging in the upper limit first, I have tangent of pi over 3 minus pi over 3 minus the quantity tangent of 0 minus 0. All right, so hopefully you have been practicing your unit circle and you are able to recall that tangent of pi over 3 is the square root of 3 minus pi over 3 minus tangent of 0 is just 0. So this is just minus 0 over here. So root 3 minus pi over 3 is the exact value for the answer here. And this concludes section 8.3.